Go. Hello and welcome back to the first half of 14.5 on curvature. The rest is tomorrow. So we talked about the vector R many times by now, the vector valued function. We know there is a 2D, 3D version. You can have a 4D and 5D, whatever. Now, straight line doesn't curve at all. So we can calculate its curvature to be infinity, actually. But then all other lines curve at the point. So curvature is going to be quantification, right? We're going to put the number to a curvature. And the larger the curvature, the faster the line bends, it will have a larger value. And if it's a very sluggish, slow, mild, whatever you want to call it, bend, it's going to have a low value, smaller number. So now let's start with the definition of curvature. Let vector R describe a smooth parametricized curve. If S denotes arc length, and T hat is the unit vector, the curvature is K of S is equal to the magnitude of the derivative of the unit vector. Now, this definition is good to explain the concept, but we are not going to use this formula to calculate anything because it's parametricized by the arc length. Arc length is the variable, which we don't calculate in terms of arc length. What is arc length? Arc length would be like, think about a curve on a pizza crust, right? So you don't parametricize, right? You measure in terms of inches, in terms of radius. You don't measure in terms of the arc length. Now, why is it good to explain concept with the arc length? Well, let's talk about the curvature over here. First off, I said already earlier that the straight line has infinite curvature. Now, let's take a look at a loop. So if I have some kind of a loop, and we know that in this case, the arc length would be a part of this loop. So we take a little bit of the loop, and that's your S, arc length. Now, we know that the tangent vector is going to be perpendicular to the radius of the curve, which is represented here by my blue pen. That's the tangent, unit tangent vector. So now, note that curvature is going to be how fast, this is the derivative of the tangent vector, how fast the tangent vector gets to turn. See, when there is not a lot of curvature, it's sluggish for this vector to turn? Slow, right? Because it moves, as you move point by point on that arc length, the tangent vectors are all close, and the slope of the tangent vector t changes very slowly. If you have this loop now small and there is a sharp turn, then as you move a little bit, your tangent vector changes quickly. So if you take a look at this definition here, it says that the curvature in terms of the arc length is the derivative of the tangent vector in respect to arc length. So it only is, the curvature is actually measuring how fast the tangent vector, the unit tangent vector, is changing in respect to arc length. So if there is not a lot of curvature, the unit tangent vector changes very slowly. If there is a lot of curvature, right, if the loop is small, so it bends quickly, then the tangent vector would change its value rapidly. So we understand the curvature through this formula, but we do not compute. For computation, we are using the theorem, which is curvature formula. And the curvature formula is going to be, we divide it. I'm going to give you the formula and then I will show you where it comes from. So curvature in terms of the parameter t, remember that we are integrating and differentiating, we're doing everything in terms of the parameter t. So curvature in respect to parameter t is going to be the magnitude of the derivative of our unit tangent vector divided by the magnitude of r of t. R prime, yes, the velocity. Now, this is the formula that you will be using to calculate curvature. Well, I have curvature formula as a title, so it should be clear from there. Now, the way you get this is you take your if you're interested in derivation, what you are going to do is you are going to multiply by 1 over dt. That's what you do. And what you get is t hat, well, dt over dt divided by ds dt. So the top is the derivative of t hat divided by the velocity on the bottom, which is dr prime. So that's how you derive it from the formula, from the red. To derive it from the red, you just multiply top and bottom by 1 over dt. So now I would like to calculate the curvature. So let's calculate the curvature for a straight line and see that the curvature is infinite. Curvature of the line, let's just come up with a line, say 2t, 3t, and obviously 6t. You're expecting 4, huh? Yeah. So my vector r is given as 2t, 3t, 6t. The vector r prime is given as 2, 3, 6. And we know that our unit vector t is r prime vector divided by magnitude of r prime vector. So t hat is going to be vector 2, 3, 6 divided by the square root of 2 squared plus 3 squared plus 6 squared. This is equal to 2, 3, 6 divided by, what is this? 4, it's 49, right?
Yeah.
Square root of 49. This is all planned. So we have 2 over 7, 3 over 7, 6 over 7. That's your vector t. So vector t hat is 2 over 7, 3 over 7, 6 over 7. To calculate the curvature in respect to t, we have to take the derivative of t hat and divide it by r prime. And these are magnitudes. Well, what's going to be derivative of three constants? Zeros, right? So this becomes now square root of 0 squared plus 0 squared plus 0 squared, which is one big fat 0 over something. I don't even care what this is. Well, actually, I know it's 7. 0 over 7 is equal to 0. The curvature of the straight line is 0, not infinite. The curvature of the corner of the spike is infinite. Yeah. Got that right. Great. So the curvature of the straight line is 0, not infinite. 0. Circle. Curvature on a circle. R is given as, let's go with 3 cosine t, 3 sine t, radius is 3. And to find the curvature, we have the r prime as negative 3 sine t, 3 cosine t on the r. T hat is r prime divided by the magnitude of r prime, which is negative 3 sine t, 3 cosine t divided by, in this case, 3. So t hat is equal to negative sine t cosine t. And we also keep in a bank over here because we'll need it, that magnitude of r prime is 3. Curvature is the derivative of the unit tangent vector divided by, magnitude of that, divided by r prime of t. So I have negative sine t cosine t divided by 3. Oh, there is magnitude over there. So 1 over 3, because when you square sine, right, negative sine, you get sine squared plus cosine squared. That's 1. And then square root of 1 is 1. So 1/3. We can, if you are memorizing that the curvature of the straight line is 0, you might want to memorize that the curvature of a circle is 1 over r. k of t equals 1 over r, and I'll put radius. So that's the curvature of the circle. Now you can obviously prove this formula by redoing this calculation. Instead of using 3, use capital R. Yes?
Is there any unit to the curvature?
No, it's just quantification. Yes, just quantification. Anytime you can do dimensional analysis to figure out. So length divided by length. The arc length, like radians, are really weird because we keep radians and degrees as units, but they're not units, because degrees are 360th part of a full circle. That's a degree. So 1 degree is simply one very, 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 very thin. Like when you go to the kids' parties and you have the half a slice thing. All right. So yeah, that's that. And a radian, right? For radians, you have the theta is equal to arc length divided by the radius, right? So if arc length is given in inches, which is your pizza crust, divided by inches of the radius, so the unit for theta doesn't exist actually. So we call it a radian. What is a radian? Radian is just when you do the 1 and 1. So 1 radian is when you have 1 inch, let's say, on the arc length divided by 1 inch. So you have to go into the unit circle, right? So the radius is 1 inch. And then in the unit circle, you go 1 inch on the circumference of the circle, bending, right, on the circumference. So to get the arc length to be 1, and whatever angle is in there, that's 1 radian. It's really awkward measurement of an angle, but it works great with pi's to break the circle, right? Because the full revolution of a circle is 2 pi. And number-wise, it's not. It's 3.1. Pi is irrational, so it works good. Tomorrow, we'll have the second part of this lecture to deal with the normal vector and its variance. And that would be it for the chapter. Now, you voted to have exam next Tuesday, which means your quizzes are starting tomorrow morning, 6 a.m., and the quiz will be open entire day. It closes at midnight. So I'll make sure that that's up and running right now. And I will see you all tomorrow for the end of this lecture. And we'll start the new chapter. Monday, guys, I hope you will bring your labs in, right? The work you did for labs. And then we have the right side of the room, left side of the room. So those of you on the right, you know what I'm come in. And we'll go from there. Bye.